Hi friends, welcome to optimization tutorial 8. So today we are going to look at the golden section search, and essentially we are going to solve some problems and write a Python code for golden section search. I am Dr. Ganguly. Now in today's video I'm going to discuss the golden section method very briefly, look at how we can bracket the minimum point, look at how to further refine this minimum, and also we are going to write Python code for this problem. So first we are going to create an example problem with some numbers which we are then going to use to verify the Python code. Now if you have not been familiar with this method, take a look at optimization lecture 8 on the golden section method and also on the optimization playlist for the full course. So let's first review the concept of the golden ratio. Now, essentially, if you have a quadratic in the form tau square minus tau minus 1 is 0, then I can solve this tau here and tau will come out to be 1 plus minus root 5 by 2. Now, if we take the positive root here, that comes out to be 1.618033399 and so on. Because this is not a rational number, it essentially goes on and on. We can truncate it to 1.618. Now this particular number is known as the golden ratio. Now there are some interesting things that if I take 1 by tau, that comes out to be 0.618. If I take tau minus 1, you can see from here that comes out to be 0.618. And also if I take 1 minus 1 by tau, that comes out to be 0.382. Now there are many situations where the golden ratio takes place or manifests in the natural world. You can take a look at my lecture 8 corresponding to this particular video for the theoretical part of this course. I'm going to leave that lecture in the description box and also in the end screen, and you can find it in the optimization playlist also. So essentially what we are going to do is that we are going to use these two numbers in purple, that is 0.618 and 0.382, to essentially bracket or further refine the minimum point. And you will certainly notice that 1 minus 0.618 is 0.382. Now some people actually use the ratio here, that is 1 plus root 5 by 2 in the algorithms, but essentially when you are dealing with computers, why subject them to these long series of numbers out there? Because like I mentioned, this is a number which goes on and on. Instead, for our purpose, it's a good idea to truncate it to 1.618 and then use 0.382 as the second number. I'm going to illustrate this in the example today. So let us present our first question, and this question is bracket the minimum of the function given below. So we have been dealing with this function for a long time. Essentially it's this form square plus the exponential part. We are asked to use a step size increment of delta is zero point 0.5 and use the golden section method. Now you essentially get several values corresponding to q, where you can obtain alpha q and the value of the function at that particular alpha value. Now here alpha q is given by this formula. Again, look at my lecture for the derivation of this formula. And so what we do is we plug in q is 0, 1, 2, 3 and so on. We get the value of alpha q from this formula, and we also calculate the function value here. So what's going to happen in one-dimensional search is that if you have picked a proper search direction, then your function is going to decrease and then it's going to start increasing at a certain point. So essentially you can see when I plot this function, it goes like this. And so I want to capture these 3 points here, points 1, 2, 3 here, which correspond to the point where the directionality of the function's decrease has changed. So essentially the function was going down and then it suddenly started going up. Now of course, depending on the function, this may take place at a later point also, so it's not necessary that you will get it so quickly as in this particular problem, because in this particular problem we know that the minimum is somewhere near 0.35. So now what we do is that we have bracketed the minimum point at which q was 3, and so we obtain the value of alpha u and alpha l as the upper and the lower bound on the region I. And so I have these two values here. Alpha L is 0.1309, alpha U is 0.473586. I calculate I as 0.342, and interestingly I can also get I from this formula which we have presented in the lecture. That also comes to 0.342686. So essentially the calculations I have done in the previous problem, they have been correct, or the previous slide. So I can then get the estimate of the minimum point alpha star, and that comes to 0.302243. Now you probably recall that in tutorial 3 for optimality criteria we had obtained alpha star, the exact solution in terms of the Lambert W function, and that was 0.351734. So we are close to it but not very close. So we have to now do some more math which is actually required by the golden section method. So what we do is we create these two new points, that is alpha A and alpha B, and these are at distance alpha L plus 0.382i and alpha L plus 0.618i. So this is where you can see how the 0.832, 0.382 and 0.618 values are being used. I get these two numbers here. Now, if I were to put it on a number plane, I would get something like this. So remember, we bracketed the minimum between these two blue circles, and now we obtained these two new points from these two formulas here. Now, of course, this graph is not to scale, but it does show you the kind of points which are out there. Now, I can immediately calculate the function values at these points. Remember, the function is given by this expression here. So I get the corresponding values here. So let us simply write down the values we have obtained. So we had the two endpoints, we had the 2 points in between given by alpha A and alpha B. We have the function values in red. Now in golden section search lecture 8, I have given 4 different conditions, or I would say several conditions which need to be looked at, and depending on that, the bound which you have or the range which you have can be reduced. So essentially in this particular case, we see that f of alpha A is greater than f of alpha B. So if you look at these two values, you will see that. So from there, I can conclude that alpha star will lie between alpha A and alpha U. Now I have shown this graphically in the lecture 8. So take a good look at that particular graph. It's going to help you figure out how we have come up with some of this math here. So in this case, this condition is true, then I can set these values of the lower bound, the upper bound, and the point A. And I put the superscript 1 here to simply show that these are the new values. Now, what we have obtained at this point in green is that the alpha star has been bracketed. We have refined it to 0.26 and 0.47, and these are the three values we have obtained here. Now, the next thing we do is we simply write down those three values here, and we also need to calculate alpha B1. And so we calculate that. That also requires this 0.618. So you go to the leftmost point, alpha L1, you add 0.618 into the new I here, or the I1. So I1 is 0.2118, and so we have done that here. So now we have obtained the alpha B1 point also, and we have obtained the value of the function at this point. Now, why I'm doing all this is that because when we write the Python code, we can check some of the numbers which are printed out by some of the numbers I have obtained by hand calculation. This is generally a good practice whenever you are trying to code in some algorithm. You want to have some actual numbers here with which you can check the veracity of the algorithm, because sometimes some bugs can creep into your program. So now the alpha star becomes 0.3676, pretty close to the actual minimum point, but still not exactly there. So let us see graphically what has been happening. So essentially we first started with this big bracket here between 0.1309 and 0.4735. Remember, we did a pretty rough search with golden section, and therefore the first round is pretty rough. But one advantage of golden section is that it converges relatively quickly compared to, for example, the bisection method we discussed before. So the next point was calculating these two values, alpha A and alpha B, and then we actually reduce this bracket to this particular point, and or this particular region, and then we also obtained alpha b1 here. So we now have these 4 points. So now you can see one of the advantages of this method is that you get to use the previous point, you do not discard it. So remember that you have this point, you have the function value at that point, so that's useful, and you introduce a new point at which you may need to calculate the function value. So then what we do is that we drop the superscript 1. So we essentially now have these new values here. So alpha L is 0.26, alpha U is 0.47, and the points in the middle of these two or inside that particular domain are alpha A and alpha B. I is 0.2118, alpha star is 0.36. So there has been certainly some reduction in I. That is the way we are going to track this algorithm. We want to bring I down to some very small value, for example, 0.001 or something like that. Question 2 is the main question which we have been preparing for today, which is to write a Python code to implement the golden section search, and we are going to test it with our usual function. So let us first write the main code. So in the main code, I am going to bring in numpy because numpy is required to calculate the function value. I am also going to essentially define two functions. One of them is the bracket minimum function, which works for the first time and brackets the minimum between 2 points. And here I'm going to give a very large number n. So this particular function is going to go on and on till the function is or the minimum is bracketed, and delta is zero point 0.05 here, and a starting value of a is 0. That's the leftmost edge at which the function is there. So once I have bracketed this minimum, then I bring in the golden section search, which takes the values from this function here, that is AL, AU, and I. And also it's going to go through this some 25 times. So I put it here. It's going to break out if it doesn't need all 25. So remember, here also I have a break statement. These are just some maximum numbers which will make sure that this algorithm goes on for some time. Now, of course, if you are dealing with realistic problems, you may have to do some kind of numerical experiments to get these numbers right. I put a tolerance value of 0.001 to basically control the convergence of this method. Now let's look at each of these functions in detail. The simplest function I have is the function f of x, which simply returns the function back to me. Now, of course, here I have to use numpy because exponential requires numpy in Python. Remember, this is not Fortran's, exponential is not built in. So then we look at this second function, define the bracket minimum function. Now here what I do is I go from j is 0 to n, and I calculate these values of the lower point, the middle point, and the upper point. And you remember the formula we were using, that is delta into 1.618 to the power j, and essentially you have to sum this up over all the values. So that's what we are doing here. The a is al ensures that summation. Now of course I put the conditions here that if you have gone beyond the minimum point and your previous point was greater than the current point, then you essentially declare that a star is the value here. You have bracketed the minimum point between these values, and you have calculated an estimate of the minimum and also the value of I. Then you return AL, AU, and I. Now remember, in Python actually you can return multiple values of numbers. So we can call this function later, and we have to essentially give these three values and then say this is equal to bracket minimum. So you can see that in my previous slide how I have called this particular function or invoked this function. So let's come to the main function here, that is golden section search, and here I essentially have the numbers AL and AU coming in, and what we do is that we essentially calculate AA and AB. Remember, these are all values which are directly correlated with the mathematical values I have discussed before, and also which we have discussed in the golden section lecture 8. So essentially then I bring in the algorithm here. Remember, in Python I can actually write multiple commands like this provided I separate them with semicolons, and so I essentially define AL1, AU1, AB1, AA1 if this particular condition is satisfied, else I define these conditions. Now you can understand this particular algorithm using the graphs I have given in lecture 8. That's the best way of figuring this out. So what's happening if the condition f AA is less than AB is satisfied, then a certain set of changes take place, else a different set of changes takes place. And once you have made those changes, you then define A star as AL1 plus AU1 divided by 2 or in 2.5, and also the new I value as AU1 minus AL1. So then we finally print out the values of the K we are at, the A star, the I1, and we have bracketed the minimum between AL1 and AU1. Now this process keeps going on and on. This is a for loop. So we need to break out of it sometime. So we break out of it if I1 is less than tolerance. Remember, tolerance is a small number. We have selected 0.001. So at that point, we essentially break out of the for loop. So we have the break statement here. Else we drop the superscript 1, just like I mentioned in the example problem we solved, and also we have given in the lecture video. So essentially what happens is that AL, AA, AB, AU and I are all set to the starting values, and then this thing goes on and on till the algorithm has converged. So let's see how this actually comes out. Here I have printed to you the output in the program. Now I wrote this entire program in Google Colab. It's a very nice place where you can do these kind of things. You can of course also download Python. It is free and you can essentially use it. So you can check some of these values are exactly the same as what we obtained by our hand calculation when we solved the example problem in 1. So you remember you had that 0.1309 and 0.4735, and the middle point was 0.26 something, and then we had the minimum and the I values as this 0.30 and this is the I, and then as we keep going on you can see the minimum point essentially ends up becoming 0.35178, which is very close to the actual minimum 0.3517. So this is pretty good as far as most algorithms are concerned. You also see how this bracket progressively gets reduced in a very nice manner. So as you take those midpoints, or I should say the points in the middle, point somewhere in the middle, that alpha A and alpha B, then what keeps taking place is that you keep checking the function values at those points, and depending on the function values, the left side of the bracket gets dropped or the right side gets dropped, and the interval progressively shrinks. So you can see from here the pretty large values which were there, 0.26 to 0.47, then it becomes 0.26 to 0.39, and so on. It continues all the way till finally it's become 0.351 and then 0.352, and here you can see the I, or the difference between these two numbers, has become very small. It is now 0.0006. So essentially it has become less than 0.001. So essentially the tolerance is satisfied now and the break statement gets fired up. So essentially what happens is that it doesn't go through all the iterations which were prescribed in the for loop. At the end of K12, or when K reaches this value, it essentially will get out of the loop and give you the optimal value here. So today we have seen how the golden section method, sometimes called golden ratio method, golden section search and so on, is a very good method as far as one-dimensional search is concerned. And the previous method which we discussed, the bisection method, where the intervals were exactly same, that was of course a very simple method. Golden section method is somewhat better, I should say much better, because it moves forward in the design space by taking increasingly large steps. So the process of finding the minimum, or at least bracketing the minimum, is relatively quick. And then after that it uses very interesting set of rules derived from the golden ratio to actually zoom further. Now you can easily write Python code to do these kind of methods. Now if you are somebody who is planning to learn Python, remember that optimization is a good place to figure out how to learn scientific Python. So that's something which you can do, and of course these kind of unidimensional methods provide the way to write various algorithms out using simple scalars. So this is a way to get an idea about the way functions work in Python, about the way different numerical methods work and so on. Now, golden section or golden ratio is certainly a very efficient method, and it is very often used in the different 1D search algorithms. Now, in the next lecture, I'm going to talk about the quadratic search, which is actually quite popular. Sometimes people combine golden ratio with quadratic search. Quadratic search would require you to bracket the minimum and then invoke quadratic functions which are there, and then basically find the minimum of quadratic functions. So again, you need some method such as the golden ratio to figure out where the minimum point lies. Now, the functions we are dealing with are quite simple. So the minimum point was at 0.35, but you can imagine a function. Let us say we create a function whose minimum point is at 10,000. Then of course you will have to use some kind of basic mathematics to figure out some approximate idea about where the minimum lies before you begin a search using delta. Delta is 0.05, will not be very good there. So these are certain things which are important. Sometimes graphing the function is very useful, having some concept about the function is very useful, and so on. So that's something which we are going to look at later. One thing to keep in mind is that very often you can scale the different problems involved. So scaling the different design variables often helps your numbers be in reasonable regions such as between 0 and 1, and that certainly helps the algorithm processes out there. I will end this tutorial now, and I will see you in a tutorial sometime soon. Make it a point to go through optimization lecture 8 before you go through this tutorial, or if you did not do so, make sure you go through it because that's going to cement the theoretical concepts, and also go through the optimization playlist. And if you feel you need some practice in math, look at the Math Mania playlist because that gives the solutions of many different math problems which are going to certainly help you become better at basic mathematics and become better at optimization also, because I have some optimization problems which are enclosed within that particular Math Mania playlist.